Okay, we're looking at section 9.4. This is geometric probability. Definition, geometric probability is probability based on areas and lengths. Okay, so let's review what's probability. So probability would be like when we roll a dice. Okay, so for example, the probability of getting a 3 on a dice is 1 out of 6. Your top number is the number of ways the event can occur. And then the bottom number is the, well, let's go total number. Total number of outcomes. Okay, so in this, for example, there's only 1 3 on a dice, so there's a 1 on the top number, and then there are 6 sides on the dice. Probability of even number, for example, well, there's 3 possibilities. You could have 2, 4, or 6. So I have 3 out of 6 sides, which would then reduce to a half. Okay? So we're going to do the same thing with probability, but now we're going to involve area and length. So for example, find the probability of choosing the pink area, use the eraser tool to check your answer. Okay? So we have 3 possibilities over a total of 8. So this is pretty straightforward, okay? Just like the regular probability was. All right, here we got 1 pink area. Well, if I divided this up, you can see that that would be 4 equal areas. So my probability is going to be 1 out of 4. And in this case, you can do it 2 ways. You can do it mathematically. You could say, well, if it's 120 and 120, it's got to add up to 360. So this is 120 out of 360. Or you could just say, well, it's a third of, oops, wrong tool. Or you could just say it's 1/3 of my circle. Okay, so pretty straightforward. All right, so story problem. We have a desk that's 29 inches wide and 60 inches long. On the desk is a calendar that's 17 inches wide and 22 inches long. A person randomly tosses a paperclip onto the desk, and we want to know the probability that the paperclip lands on the calendar. Okay, so what we're going to do is we're going to take the area of the calendar over the area of the desk. Okay, so the area of the calendar is going to be length times width, because that's a rectangle, right? And our desk calendar is 17 by 22. That's our top number. The area of our desk is, okay, that shape is also a rectangle, but it's 29 by 60. Okay, couple ways to do this. We could reduce before, or we could reduce after. We have a 17 and a 2 and an 11. We got a 29. Okay, so we could reduce this by 2. We'll just remember that at the end. Let's do that. Okay, so our top number would be 17 by 22, which is 374. And then we have 29 by 60, which would be 2,610. Those are both even. That means that I can reduce it by dividing by 2, so 187. And then we have 1305. Okay, and I don't believe that can be reduced any farther because we can't get 17. This would be, so 2 and 3 and 2. Yeah, so that's it. That's our answer. The probability would be 187 out of 1,305. And if we ask for that in a percent, I'm just going to divide those two numbers. So it's about 14.3%. So about a 14.3% chance that they would hit the calendar when they just randomly toss the paperclip. Okay? Here we have a parachutist that wants to land on a circular pad, okay, that has a diameter of 20 feet. If the rectangular field that it's in is 300 feet by 150 feet, what's the probability they'll land on the pad? Okay, so we have a rectangle that's 300 by 150, and our circle has a diameter of 20 feet. So we're going to take the area of the circle over the area of the rectangle. Area of a circle is pi r squared, so So we have pi, my radius would be 10 squared, over the area of the rectangle, which is 150 by 300. And obviously this one is not going to reduce. So we'll just give an approximation. So we'll go pi times 10 squared is about 314.16. And 150 times 300 is 45,000. So let's divide those two numbers. So it's about, oh, that didn't work out well. So 0.00698. So the percent of chance would be about 0.07%. So it's not even a 1% chance that they would hit that pad. Now, of course, it's also going to take into account, how good is this guy? Ability is also going to factor in. But for the straight probability, that's what we've got. Okay, here we've got a different kind of a problem. We have a cable TV service person says that they'll arrive sometime between 2 p.m. and 5 p.m. If you have to run to the store and will be gone for 20 minutes, what's the probability that the repair person will come while you're away? All right, so we can do this a couple ways. We could set up a timeline. Okay, so you got 2 p.m., 3, 4, and 5 p.m. And we want to know if we leave for 20 minutes, somewhere in between there, what's the probability that the guy's going to come? So you take your 20 minutes out of the total. So 20 minutes out of the total, which was 3, 4, 5 o'clock, so 3 hours. Now my problem here is that I have different labels, so I either have to change them both to hours or both to minutes. So let's make them minutes. 3 times 6 is 180, now we're in minutes. Now I just reduce, so 1/9. There's a 1 in 9 chance that the guy will come when you're gone at the 20 minutes. Okay, we could also make that into a percent, which of course is about 11%. And we could leave it at that. Okay, so that's pretty much it. So basically you need to know your basic area formulas, circle, rectangle, triangle, so that you can do problems like these. So make sure you've got a list of those somewhere.